Avi the puppy runs at a constant speed of 4.85 meters a second. So this is my dog. The velocity is equal to 4.85 meters per second. When Avi's at a distance, towards a stationary remote control car. So we know its initial velocity is equal to 0. When Avi is at a distance of 32 meters from this car, so let's set the x reference here as 0. And when it's 32 meters away from the car begins to accelerate at a uniform rate of 0.165, let's not forget units, meters per 165 meters per second squared. So we know the dog's acceleration is 0 because it's not accelerating. We know both of their initial x's. Here it's 0 because we're setting that as a reference. Here it is 32 because it's 32 away from 0. Let's think about what type of problem this is. There's no forces really specifically mentioned in this problem, so we can assume it's not a net force equation or a net force problem. There is not really any energy, or there's no height, there's no springs, and there is no really mention of energy, so we can assume this is not an conservation of energy problem. And we have many of the variables used in kinematics equations, so we can assume we need to use kinematics to solve this problem. So let's think about the fundamental parts of kinematics. We know one of them is in a graph of x over time, the slope is the velocity. And then we also know that in a graph of velocity over time, the slope is acceleration. These are the two of the main ideas or main concepts of kinematics, which are used to do all the problems. So using this, let's start with the second graph. The acceleration is equal to the slope of this graph, and to find the slope, we use first what would be the y-axis. We use its initial position, and then subtract. We use its final position, and then subtract its initial position. And then we do the same thing for what would be the x-axis, tf minus ti. And then if we put this more in physics terms, the final v would just call that v, and the initial v, we would call that v naught. And then the change in t, or delta t, we just call that t. We just assume it's the change in t. So now we have this, and then if we solve for v, so we multiply by both sides by t, and then we, not equal to, and then we add v naught to both sides. We get v is equal to v naught plus at. And this is our first kinematics equation. Now let's derive the second one. Let's use this first graph. We know that the average velocity is equal to the final velocity plus the initial velocity over 2. That's kind of just the definition of an average. And this is assuming that the acceleration is constant, which it is in this problem. So this we can assume this is true for the average velocity. And then we know again that the slope, or the velocity, is equal to it's equal to the slope, which we can use the same concept as the other graph. So the final will be the y xf minus xi over tf minus ti. And again, we can change this to be, let's write it down here, into physics terms. And then now we have these two things which are equal to each other, right? So now let's try to solve for x, right? So they're kind of on top of each other, which might be confusing, but let's multiply both of them by t. I'll rewrite it down here. Let's take the 1/2 to the side. V plus V naught. Again, we're simplifying this into physics terms, so this would be the XF, the VF would just be V, and the VI would be V naught. And then we multiply the top by T, and it's equal to X minus X naught. And then we add X naught to both sides to isolate the X. And we get our second kinematics equation, which is X equals X naught plus 1/2 V naught plus V T. Now we can use both the equations we have. We can plug in what we got for V in the first one in for V in the second one. So we get this V naught plus another V naught plus AT, all multiplied by T. So let's distribute the 1/2 and the T into this. So let's start by just combining the two V naughts into 2 V naught plus AT. And then let's distribute the 1/2, which would be V naught plus 1/2 AT. And this is still being multiplied by T. And then let's distribute the T. So now we get, I'll just write the whole equation for this one. X equals X naught plus V naught T plus 1/2 AT squared, because we distribute the T to both these terms. And this is our third kinematic equation, and this is what we can use to solve this equation. So from this, in this equation, we know V naught for both of them. We know, we know also X naught, and we know the acceleration for both of them. So we need to know T and we need to know X. But since we have two equations here, let's start by writing the equation for the dog and for the toy. The dog's equation is X is equal to, well, let's just use this, X naught plus V naught T plus 1/2 AT squared. And we know the X naught is 0, that's our reference. We know the acceleration is also 0, and anything multiplied by 0 is 0, so this whole term we can cancel out, which just leaves us with the V naught that we are given, which is the same as the final velocity because it's not accelerating. So yeah, so this V, I'm right, I don't know if I have space, whatever, this is also equal to V naught. So we can plug that in. X equals 4.85 T. Now let's write XD. Now let's write toy, and let's rewrite this equation. Okay, we know X naught, 32. We know acceleration is 0.165, so we can plug in these two. And the V naught is 0 because the problem tells us it starts stationary, and anything multiplied by 0 is 0, so we can cancel out the second term. X for T, which is toy, is equal to 32 plus 1/2 times 0.165 times T squared. Now, how do we find when these two objects are at the same point? Well, that would be when they're at the same X value. So I mean their x value is the same. So these two values, xd and xt, would be the same. So we could just subtract one equation from the other, because just so we would be able to cancel out these x's, right? So it'd be, I'll write the equations on top of each other and show you what I mean. 4.85 t x equals 32 plus 1/2 times 0.165 t squared. So if we subtract this from this, we could cancel out these two x's and only have one unknown left. So that would leave us with 0, because these two x's cancel out, is equal to 4.85 t minus 32 plus 1/2 times 0.165 t squared. Now let's plug this into a calculator, and it'll give us a graph of the position of the two objects compared to each other. If we just solved, this calculator, I set it equal to y instead of equal to 0, so you can actually see the distance between the two objects over time. But if you just solve for 0, it'll just give you the two points in which the two objects intercept, which is the only 2 points we're interested in. And on this graph, that would be when it passes the x-intercept, or the x axis. So we can see it actually passes it twice. And from the problem, we know the first time is when the dog misses it, and the second time it catches it. So let's write down these two. Let's write down these two numbers. I don't have much space. Let's write it in here. T number 1 is equal to 7.57, and T number 1, and T number 2 is equal to 51.21. And let's not forget our units. These are in seconds. This would be the two values for the first part. Now let's make some space and let's get to work on the second part. So below a certain minimum constant speed, Avi would never catch the toy car. What would Avi's minimum constant speed need to be to have exactly one attempt to catch it? So let's think about this. The way I like to think about it is in vertex form. Vertex form is when y equals x minus a certain value plus a certain value. This first certain value would be the position of the vertex on the x-axis. So if it's negative, it'll be in the positive area because it's subtractive. And if it's positive, it'll be in the negative because it's subtracted. So we're not as interested in that. We're more interested in this point, because when this is positive, the vertex is above the x-axis, but when it's negative, it's below. But when b, this value, is at 0, there's exactly one intercept on the x-axis, which is what we're looking for in this problem, because as you saw from the graph I showed you, when there's only, the points that intersect the x-axis are the points in which the toys are at the same point when you subtract one equation from the other. So let's write down the equations we have for this part. They're mostly the same. For the dog, we don't know the velocity anymore, so we know x is equal to vt. But for the toy, it's the same equation. It's equal to 32 plus 1/2 times 0.165 t squared. So we know, again, we're setting these x's equal to each other. so we can just subtract one equation from the other. For simplicity, let's actually subtract the dog from the toy. So this would be this one minus this one, which would be 0 is equal to, the x's cancel out again, 0 equal to 32 plus 1/2 times 0.165 t squared minus vt. Let's put this into a more clear form. 0 equals, we'll put the t squared first, and then the one with the 1t, vt, and then no t. So let's think about how to, okay, important thing I forgot to mention, this is squared, because we're dealing with quadratics, my bad. So how we would expand something like, let's just use a and b, like a minus b, how would we expand that squared? Let's put this into a box, a minus b, a minus b. The a term would be squared, a times a, then it would be a times negative b, so negative ab, and then again a times negative b, so negative ab, and then negative b times negative b is positive b squared, so this expanded would be a squared minus 2ab plus b squared, and that's what we have this form in right now. So now we would have to work backwards to put this into a form in which there's no b. So we would have to turn this into just an a minus b squared form. So how would we do this? Well, we know this first term here, 1/2 times 0.165 t squared is a squared. So to work backwards to find a, you would find the square root of this term, this first term. So in the first thing in these parentheses is square root of 1/2 times 0.165. And then there would be a t squared inside of the square root, but then we know that the square root of t squared is t, so we can actually take that out of the square root real quick. Change this to 1/2, excuse my tilted writing, 0.165, oh Jesus. Okay, and then the second term would be subtracted, and again, how would we find the second term? Well, we know that the third one here is b squared, so work backwards, we find the square root of it, so minus square root of 32. All that's left is this middle term, negative 2ab. So we know a and b, so basically we just have to multiply 2 times square root of 1/2 times 0.165 t times negative, or not times negative because we already, okay, this is all negative, square root of 32, and that would give us this middle value in which we have the unknown. So I'll plug that really quick into my calculator, and we would get negative 0.325, and that would be equal to this middle term, which is negative vt, 0.5t, and they both have t in it, so we can divide both sides by t, cancel that out. So negative 0.325 is equal to negative v. So again, we can multiply by -1, take out that negative, and we get the velocity. Velocity is equal to 3.25. And then, of course, let's not forget the units. Meters per second. Oops, on this. So that's the answer to the second part. We can use vertex form to find when there's only one time in which the two objects intercept, and then we can use that to solve for the velocity. Hopefully that was clear and helped you understand.